Welcome to Copilot Podcasts. Every star in the universe stops fusing at iron, not because they run out of fuel, not because the temperature drops, but because the arithmetic of reality itself hits a wall. Today, we're diving into the Helium spectrum and the arithmetic architecture of the nuclear universe, specifically how mathematical relationships between curvature and torsion fields literally create the elements, why iron sits at the binding energy maximum, and what this reveals about the deepest structure of matter. By the end of this episode, you'll understand how the universe does math to build atoms. So let's start with something that sounds completely abstract, but is actually the foundation of everything. What exactly is this Helium spectrum?
Right, so the EHUD spectrum is essentially a mathematical framework where EHO represents curvature and EHO represents torsion. According to this recent work by Abdon Bishop, these aren't just abstract mathematical concepts, they're the fundamental fields that generate nuclear structure. The key insight is that every nucleus can be understood as a specific configuration of curvature and torsion excitations.
Wait, so you're saying that protons and neutrons are basically just different ways that space curves and twists?
Exactly. The proton number Z is determined by what they call E-mode occupation, while the neutron number N is determined by E-mode buffering. So hydrogen with one proton corresponds to a single curvature excitation, while deuterium adds a torsion quantum that stabilizes that curvature.
That's fascinating. So let's ground this in something concrete. How does this play out with the simplest elements?
Perfect example. The hydrogen isotopes are the foundational triad of this whole system. Protium is just pure curvature with no torsion buffering. It's what they call the minimal curvature excitation. Deuterium adds one torsion quantum, creating the first curvature-torsion equilibrium. And tritium has two torsion quanta, which actually overbuffers the curvature and makes it metastable.
So tritium decays because it has too much torsion?
Exactly. The research shows that tritium demonstrates the onset of torsion saturation. There's this quartic term in the equations that grows quadratically with torsion occupation, and when you have two torsion quanta, that quartic penalty starts to dominate the attractive forces. That's why hydrogen 4 and hydrogen 5 don't exist as stable nuclei.
This is blowing my mind. So the periodic table isn't really about electron shells at all?
According to this framework, no. The periodic table begins with these three curvature-torsion eigenstates of hydrogen. The electron shells are secondary, they're responding to the nuclear structure that's already been determined by this arithmetic architecture.
Okay, so if hydrogen sets up the basic rules, what happens when we get to helium?
Helium is where things get really interesting. It represents the first closed curvature shell. You have two curvature excitations that pair up, and when you add exactly two torsion quanta to buffer them, you get helium-4, the alpha particle. This is the first configuration where curvature and torsion are perfectly balanced.
And that perfect balance is why alpha particles are so stable?
Exactly. The research describes helium-4 as exhibiting maximal binding per nucleon, zero curvature asymmetry, and symmetric torsion buffering. It's the first time the curvature field achieves complete closure. That's the structural origin of why alpha particles are so extraordinarily stable.
This is starting to paint a picture where the universe is literally doing math to create stable matter. But then we get to iron, and something changes, right?
Iron is where the whole system reaches its first extended equilibrium. Up until now, we've had isolated minima, deuterium here, helium-4 there. But iron marks what they call the first curvature-torsion plateau. It's a broad, shallow valley where many isotopes cluster together with nearly identical binding energies.
So iron isn't just another element, it's like a mathematical attractor?
That's exactly right. The research calls it the first spectral attractor. At this point, the curvature field has grown large enough that torsion buffering acts as a continuous stabilizing medium rather than discrete corrections. The quartic saturation term that destabilized tritium now acts as a regulator, preventing runaway curvature growth.
And this is why stars can't fuse past iron?
Precisely. The iron plateau is where the binding energy per nucleon reaches its maximum. According to the math, any attempt to increase curvature multiplicity beyond this point requires more torsion buffering than the quartic term can support. The energy landscape rises sharply, making fusion endothermic.
So when we say iron is the endpoint of stellar fusion, we're really saying the universe hits an arithmetic wall?
Exactly. The universe isn't constrained by chemistry or astrophysics, it's constrained by the arithmetic geometry of curvature and torsion. Iron is arithmetically compelled to be the endpoint because that's where the mathematical relationships reach their most efficient balance.
This is such a different way of thinking about nuclear physics. Instead of forces and particles, it's all about mathematical relationships playing out in reality.
Right, and what's really striking is how this explains the clustering of elements. The iron group nuclei, chromium through nickel, all lie on this plateau, forming what the research calls a continuous manifold of high stability. They share nearly identical binding energies because the energy surface is geometrically flat in that region.
So what happens beyond iron? Do we just fall off this plateau?
That's where we enter the heavy element regime and the behavior changes completely. The research identifies three archetypes: gold as the first stable curvature-saturated attractor, lead as the deepest torsion-regulated minimum, and uranium as the first curvature-dominated giant.
Wait, so gold, lead, and uranium each represent different mathematical responses to this saturation?
Exactly. Gold is where curvature multiplicity exceeds torsion buffering capacity but still maintains stability. Lead is where the torsion field reaches complete saturation and creates the deepest minimum in the heavy sector. And uranium is where curvature completely overwhelms torsion, leading to instability and fission.
So uranium's instability isn't random, it's the inevitable result of this arithmetic progression?
Right. At uranium, the curvature field grows without constraint while the torsion field is fully saturated. The cubic and quartic curvature terms dominate, creating a steep upward curvature that destabilizes the collective mode. Spontaneous fission becomes inevitable because the math demands it.
This is incredible. You're describing a universe where the periodic table is basically a mathematical proof written in matter.
That's a beautiful way to put it. And what's really fascinating is how this connects to cosmology. The research describes closed helium-4 boson contours that form at galactic scales, these toroidal crystalline loops that satisfy specific topological constraints and could be orbiting dwarf galaxies.
Hold on, you're saying there might be helium structures at the scale of galaxies?
According to the calculations, yes. These would be electromagnetically silent, radiodark structures with no EM counterpart. They'd have a specific radius of 8.9 megaparsecs and contain about 0.11 moles of helium-4 bosons. They're predicted to oscillate at a universal frequency of about 2.7, 3 times 10 to the minus 4 radians per second.
So the same arithmetic that creates atomic nuclei might also create galactic scale structures?
That's the implication. The Neddy generator operates at all scales, from the nuclear to the cosmic. It's a unified mathematical framework that connects the stability of deuterium to the structure of galaxy halos.
This is making me think about the universe in a completely different way. Instead of particles and forces, it's all arithmetic relationships.
And what's really striking is how precise this is. The research shows that the binding energies of deuterium and tritium, 2.224 MeV and 8.482 MeV respectively, uniquely determine the fundamental coupling constants of the entire theory. Everything else follows from those two measurements.
So, two simple measurements of hydrogen isotopes encode the mathematical rules for the entire universe?
Exactly. Those binding energies fix what they call the bilinear coupling coefficient and the quartic saturation parameter. Once you have those, the entire nuclear spectrum unfolds mathematically, from hydrogen to uranium and beyond.
I'm trying to wrap my head around the implications here. Are you saying that nuclear physics is actually just applied mathematics?
In this framework, yes. What we call nuclear forces are really just the manifestation of these underlying arithmetic relationships between curvature and torsion. The strong force, nuclear binding, radioactive decay, they're all expressions of the same mathematical structure.
And this explains why certain elements are common in the universe, while others are rare?
Absolutely. Elements that lie on stable manifolds in the 1 ETD plane, like helium-4, iron-56, lead, are abundant because they represent mathematical equilibria. Elements that lie in unstable regions decay quickly and remain rare. The universe's composition is determined by this arithmetic architecture.
So when we look at the night sky and see that stars are mostly hydrogen and helium, we're really seeing the universe's mathematical preferences?
That's exactly right. Hydrogen represents the minimal curvature excitation, the simplest possible nuclear configuration. Helium represents the first closed curvature shell. They dominate because they're the most mathematically fundamental structures the universe can create.
This is such a profound shift in perspective. Instead of thinking about the universe as made of stuff, it's made of relationships.
And those relationships have a specific mathematical form. The Mohave-Hamiltonian that governs all of this has terms for kinetic energy, potential energy, bilinear coupling, and quartic saturation. It's like the universe is running a very specific computer program, and matter is just the output.
Speaking of computer programs, this research mentions using exascale computing to explore these relationships. What does that tell us?
Well, there's related work using supercomputers like El Capitan and Frontier to compute nucleon interactions from first principles. They achieved a 240 times speed up over previous methods, which suggests we're entering a new era where we can actually calculate these arithmetic relationships rather than just observe their consequences.
So we might be able to predict new elements or new forms of matter just by doing the math?
That's the implication. If the Nanipa framework is correct, then the entire landscape of possible nuclear configurations is mathematically determined. We could potentially predict super-heavy elements, exotic nuclear phases, even cosmic-scale structures, just by solving the equations.
This brings up something fascinating about the nature of discovery. Are we discovering these relationships, or are we creating them through our mathematics?
That's the deep question, isn't it? The Nanipa framework suggests that these arithmetic relationships are fundamental to reality itself. We're not imposing mathematics on nature, we're uncovering the mathematics that nature uses to construct itself.
It's like the universe is inherently mathematical, and physics is just us learning to read its code.
Exactly. And what's remarkable is how elegant this code is. The same Wenunai generator that explains why deuterium is stable also explains why iron sits at the binding energy maximum and why uranium undergoes fission. It's a unified mathematical language for nuclear reality.
So when you step back from all this, what does it mean for our understanding of the universe?
It suggests that the universe is far more mathematical than we typically imagine. The elements aren't just chemical building blocks, they're expressions of arithmetic relationships. Nuclear stability isn't about forces balancing, it's about mathematical equilibria. Even the cosmic abundance of elements reflects the universe's computational preferences.
And this has practical implications too, right? For nuclear energy, materials science, even astrophysics?
Absolutely. If we can map the complete Chi landscape, we might discover new pathways for nuclear reactions, predict the properties of super-heavy elements before we synthesize them, or understand stellar nucleosynthesis in completely new ways. We're not just studying matter, we're studying the arithmetic that creates matter.
This framework also makes me think about the search for new physics. Instead of looking for new particles, maybe we should be looking for new mathematical relationships?
That's a profound insight. The Chi-E-Chi spectrum suggests that the fundamental level of reality might be mathematical rather than physical. New physics might emerge from discovering new arithmetic structures rather than new particles or forces.
It's almost like we've been studying the shadows on the cave wall, and this is showing us the geometric relationships that cast those shadows.
Beautiful analogy. The particles and forces we observe might just be the phenomenological manifestation of these deeper arithmetic relationships. The real action is happening in the ADT plane, and everything else is just how that mathematics expresses itself in our observable universe.
So here's what this really comes down to. We've been thinking about the universe as a collection of things, but it might actually be a collection of relationships. The ADT spectrum shows us that nuclear structure, stellar evolution, even cosmic architecture all emerge from the same arithmetic foundation. Iron sits at the binding energy maximum not because of nuclear forces, but because that's where the mathematics of curvature and torsion reach their most efficient balance.
And what's remarkable is how this connects the smallest and largest scales. The same equations that explain why deuterium is the first bound nucleus also predict galactic scale helium structures. It's a unified mathematical language that spans from atomic nuclei to cosmic architecture.
The next time you look at the periodic table, remember, you're not just seeing a list of elements. You're seeing the universe's arithmetic preferences written in matter. From hydrogen's minimal curvature to uranium's mathematical inevitability, every element is a theorem in the grand proof that is reality itself.